or sorry, the second term is going to have to be positive. You've got 1 here. To get to the real compression factor, you're going to have to add a little chunk to it. And so you use this guy to add the chunk to it. If you're still not, or if whatever term you use there sent you over, then you can subtract a little bit with the next term. And if you still haven't quite gotten to the number, you can use as many terms as you like down the road until it fits perfectly. This term, if z is less than 1, is going to be negative, right? To bring that compression factor down to something that's less than 1. So essentially, you can generate an equation of state using your series expanded compression factor, and I'll show you how we get there. So we start off with our z. We derived an expression for it based on ideal gas theory. It's P times the real molar volume divided by RT. We set that equal to our series expansion. And then you move the RT and the V over to the other side of the equation, multiply by RT, divide by V. And you end up with this term right here. And if you change the molar volume and say that the molar volume is N over V, and then plug that N over V term in every time you have the molar volume term, your equation turns into that form. So the pressure is equal to nRT over V times that series with the different terms. And that becomes your virial equation of state. Yeah? So those two equations of state just basically are different mechanisms for correcting for non-ideal behavior, right? It turns out that the virial equation of state is the most precise simply because we can make it as precise as we want by using as many terms as we want. The van der Waals equation is not as precise, but it's a little simpler to use because we always only have 2 terms that we have to deal with instead of having an infinitude of terms. Series expansions become very important, especially when you start wanting to interpret signal from objects. But you'll find that out as you go along. Real quick, we're going to get into this stuff a little bit later in subsequent chapters, but since your book does discuss it in chapter 1, we'll just mention it briefly. There was behavior that was not predicted by ideal theory, that is caused by attractive forces that molecules feel and repulsive forces. There's 2 sets of behavior we'll look at. One of the things that gases do that ideal theory doesn't predict is that they condense, right? If you get gases at low enough temperature or high enough pressure, those attractive forces grow. And some gases, if the attractive forces are dominant, will turn into a liquid, right? So ideal theory doesn't predict that, but that's something that does happen in real gases. You have their condensation. Another piece of behavior that your book talks about, just go ahead and read the chapter, read it in its entirety. It's not a waste of time. Is the formation of supercritical fluids. And supercritical fluids are gases that won't condense. You can increase the pressure on them on the outside as much as you want, and they'll never go into the liquid state. And it's because the temperature is high enough that each gas molecule on average has enough kinetic energy to avoid being captured by its attractive forces with other molecules. So at a high enough temperature, if the temperature is past a certain amount, you won't get gases to condense. And the temperature at which the gas ceases to have the ability to become liquid is called the critical temperature. And a fluid that is a gas past that critical temperature is called a supercritical fluid. Supercritical fluids are used in a lot of extraction. You can use supercritical carbon dioxide to pull out a lot of organic compounds from plants and food sources and et cetera. And so supercritical CO2 doesn't offer the same hazards that like an organic solvent or something like that would display. An organic solvent, depending on what the solvent was, you try to extract something with it and you got residual solvent left, and all of a sudden you got lumps growing on your skin where you didn't want them. But supercritical CO2 will extract the stuff, and then as soon as you vent it, the CO2 pops out in the gas phase and you're left with a pretty clean sample. All right, let's take a look at homework. I'm just going to go over each problem quickly, and I'm going to turn you guys loose and hope that you will start solving them yourselves. The first couple questions are just kind of like dumb review questions that you might have answered in Gen Chem. You'll notice that on this thing I've posted a lot of the answers. I haven't shown the work to get the answer. Obviously, if you turn in homework, you want to have the work included with the answers. Perfect gas undergoes isothermal compression. The volume's reduced. The final pressure and the final volume are 5 bar and 4.65 liters. Calculate the original pressure of the gas in bars and atmospheres. Basically, you're just going to be taking your ideal gas law, your PV, NRT, and you're going to be looking at those relationships between volumes and pressures. That should be a fairly simple problem to solve. And number two, you've got a tire, and it's got some gas in it at one temperature, and you've got a known pressure. Basically, you've got a defined state of that system. A constant volume situation, and you move it into a new state where the temperature has changed and the pressure is going to change. So again, this is just going to be one of those things where you take PV equals NRT and you look at the initial and the final conditions, what has changed, what hasn't. In this case, volume is constant, so the volumes will come out of the equation. And so you just set the equations equal to each other and solve for the thing that you're missing. Not a difficult problem. In fact, if I had more time, I would have taken the time to write a better problem. Here you're just calculating density. And so you've got O2, they've given you pressure and temperature. Pressure and temperature is going to allow you to solve for number of moles. It's number of moles, you know it's oxygen, so you can multiply number of moles times molar mass of oxygen. That'll give you the total mass. And then for the density, you divide that mass by the total volume, right? On number 3, and you're done. So that one is also a very easy problem. Number 4, okay, so this one, okay, yeah, sorry, I was reading too fast. I didn't see that they mentioned it was nitrogen. All right, so this one asks you to use the Van der Waals equation, right? We built the Van der Waals equation. P is nRT over V minus NV plus the minus A times N over V squared. You're going to look up the constants A and B for nitrogen gas. And once you have those constants A and B for nitrogen gas, you can plug in the rest of the values that they give you and solve for that pressure at 500 Kelvin. All right, so number 4, you're going to have to physically look up those constants in your textbook in order to solve that. 5 is another easy one. I stole this homework assignment from another instructor. Some of these are too easy, but at the same time, they're nice warm-ups. 5, you've got 2 separate containers, each that have gas in them. And they are separated by a stopcock. And they're not at the same pressures and temperatures, right? They're at different pressures and temperatures. They have different numbers of moles. You pull the stopcock, you open that guy up, the gases mingle. Yeah? Now you have a volume that is the sum of the 2 volumes that you started with, and a number of moles that is the sum of the 2 numbers of moles that you started with. So total number of moles is going to be number in here plus number in here. The new volume is going to be the sum of those 2 volumes. Once you've got that figured out, you can basically just plug in the values and find out what the total pressure is going to be, and what the partial pressure for each species would be. And so that problem requires that you remember whose law is that the total pressure is the sum of the partial pressures. Who do they give credit to that for? What's that? Somebody's. I forget exactly. I've been teaching chemistry for almost 10 years now, and I don't remember any of this stuff. And I'm proud of myself for that. One of those guys. Somebody got credit with that, and they still want to shout out to him all the time. Okay. What's that?
I'm trying to remember who.
Dalton's law. Dalton's law of partial pressures. See, I'm not as bad as I claim to be. So number 6 gets you back into the compressibility factor thing that we talked about. So it's the ratio of the observed molar volume to the ideal molar volume. It tells you that the ideal volume is 12% larger. If the ideal volume is 12% larger, are we looking at a compression factor that's greater or less than 1? If the ideal volume is larger than the actual volume, is the compression factor greater or less than 1? What's the compression factor? Compression factor Z is equal to the molar volume divided by molar volume of the ideal gas, right? So if this is larger than this, we're looking at a Z that's less than 1. So we've got a compression factor in this guy that is less than 1, and they want you to figure out what the molar volume of the gas is and which forces are dominating in the sample. So we just had a discussion about that, so you guys should probably be able to answer which forces are dominating just based on what we talked about here today. All right? That was a tricky problem. You might have to end up coming to talk to me in office hours a little bit. There's a little bit of a trick to it. Chapter number 7. Calculate the values of the root mean square, the most probable speed, and the mean speed for argon at 298K. So we generated all those equations using the Boltzmann distribution of molecular speeds for root mean square speed, the average speed, and the most probable speed. Yeah, we did that one too. So just basically go reference those equations, pull them up, figure out what the molar mass of argon is, right? What the temperature is. They're doing it at 298 Kelvin. It's pretty much plug and chug from there. Just throw in the right variables and spit out the answer. 8 is really tricky, and I almost don't even want to have this problem up there, but again, I didn't have time to write a new one to replace it, so it is there. What 8 asks you to do is this. You got your Boltzmann distribution of molecular speeds. It's m over 2 pi kt halves times v squared, I think there's a 4 pi out here, v squared e to the negative m v squared over 2kt dv, right? And so that is p of v, probability of having some speed v is equal to this. Now, this kind of is asking you to use a technique that you might not have used since the first time you took calculus, and that might have been a while for you, some of you, so we'll just show you what the technique is. If you want to estimate what the value is for this, instead of integrating between points, what you can do is you can just figure out, you got a curve. Let's draw this. Let's say that we're examining this probability of finding the molecule at whatever this particular velocity is, v, right? The probability is proportional to the volume inside whatever that sliver is, yeah? And you can integrate that, accounting for infinitesimal changes, or you can just estimate and say, well, if I know what my delta v is here, and I know what the probability is, then what I can do is I can figure out an average v, right? So your v, we're looking for the probability that v lies between this velocity and this velocity. So to run the estimate, we're going to take the average velocity and we're going to start plugging into these equations. We'll say that p of v average for these guys is equal to 4 pi m over 2 pi kt, 3 halves, times that, it's not average, it's the median. Is it median? Is that the right language? Yeah, I'm not sure how to mark that. Anyway, so it's a v squared term, but instead of integrating over the v's, we're just going to plug in the value that is right between these bars. And then instead of plugging in dv here, we'll just determine dv from the problem. You're running a range between 290 and 300 meters per second. So this guy here on this side is 290, this guy is 300, right here in the center is 295. So you're going to take your velocity that you plug into this equation and just throw 295 in on top of it, and then your dv is the range. dv is, you move from 290 to 300, so it's 10 meters per second for dv. And essentially just plug those values in, the 295 for v, the 10 meters per second for dv, throw them into your equation, and you should get a probability from that, right? So it's an alternative to integrating. It's not the perfect estimation, but it does a close enough job. And that's all you got to do for this guy. Nine just asks you to know how the Boltzmann distribution changes with temperature. We already discussed that. We increase the temperature, we've got more energy that we have to store in our particles, and so we're going to have to move them all to higher energy levels. So we're going to shift that distribution towards higher energy levels to consume the extra energy that we gain when we increase the temperature. You don't have to answer that, what is the approximate value for C most probable part. You don't have to answer what it would be. Okay. Now 10 is the fun part. 10 is the part where we actually don't get away from the calculus. And I think that I'll probably encourage you guys to work on problem number 10 now in class as opposed to the other ones that are easier. But you've got your distribution of velocities. 10 asks you to derive the mean speed. We already looked at how to set this problem up in lecture, right? The average values theorem tells us that if we take the probability times the probability by the value and then integrate over all possible values and probabilities, that we end up getting the average value, right? Remember that conversation? We talked about how to use the Boltzmann distribution. So, so for this guy, we're taking our probability, which has a term of v squared e to the negative mv squared over dv, multiplying it by the value, which is just v, and so sorry, I didn't read the problem closely enough. They're talking about they're asking you for the square speed, the root mean square speed, and so we multiply the probability times v squared, integrate over all possible values, and then take the square root of that to get our root mean square speed. So it kind of looks like this. This is using notation that we didn't use. Their S's are RVs, and so for them S means speed, for us V means speed. But basically, you get your Boltzmann distribution, your probability function, multiplied by speed squared. Take the integral. It's going to be the integral of speed to the fourth e to the negative m speed squared over RT ds, and you integrate that from 0 to infinity. And what you should get after you integrate that is the average value of v squared, which is going to be 3RT over m. And then you take the root of that to get the mean square speed. So your answer ends up being 3RT over m. But to solve this integral, you're going to need a table of integrals. And this table of integrals will be made available to you. But you'll see this covers most of the scenarios rather well. Integral from 0 to infinity of x to the fourth e to the negative ax squared dx is 3 over 8a squared pi over 8 to the 1/2, right? So when you've got a power of this guy to the fourth, you're going to use this integral, and that's what we had. We had power of speed or we had speed to the power of the fourth, right? Fourth power in ours. So basically, you're just setting up that integral and running it. And it's a lot of book work to do this problem, but it's not a very difficult problem. In the grand scheme of things. Boy, I thought we were gonna have time for study hall, and I just used up all the time, didn't I? What time are we supposed to stop?
10 minutes.
Huh?
In 10 minutes.
It's not a lot of time for study hall. Best laid plans of mice and men. It looks like that's the only problem. So let's use the next 10 minutes to solve this guy. And I'll go ahead and write this chunk down right now, and I'll pull that integral out for you too. I'm gonna go invade the Ukraine later on this afternoon, so if anyone wants to come with me, you're more than welcome. I don't know, because everybody else is doing it.
To where?
Ukraine? You guys watching the news? Nobody knows that we may or may not be on potential verge of like war with Russia, right? You guys don't know that? Really?
Did Russia
Oh, yeah,
just?
You guys are science students, and let me put in a request here. I hope that you're socially and politically aware as well as, physically aware. I'm hoping that scientists save the world. I could be wrong.
Wait, did Russia invade Ukraine?
It's they're doing it in a way where it's really hard to say, well, actually it's not really hard to say. They're claiming that it's a kind of a grassroots political movement, and that there are a bunch of volunteers that are coming out and picking up arms to fight off the fascists. But the fact of the matter is that they're putting in Russian forces and asking them to not reveal where they're from or who they are. So they're sending a bunch of Russian soldiers over, but dressing them plainclothes and saying, "All right, pretend you're a revolutionary." I don't have an opinion too much one way or the other. I think all governments are kind of screwed up, but boy.
I don't know, I've heard the opposite.
What's that?
There's actually no Russian troops on Ukrainian soil, and that it's actually is a...
I don't know what news sources you've been reading, but the majority of the news sources have a consensus that there's a lot of Russian troops that are. I mean, they've sent reporters in to interview the separatists or whoever they are, and there's footage of a reporter walking up to a soldier and asking him, what city are you in? And the guy has no answer. He doesn't know the region. He doesn't know the area.